Now we come to our last section, which is statistics. I think it's by far the most interesting. It's certainly the most relevant for you. Probability and statistics, the two, they go together, of course. Probability is the theory, but statistics is really, in some sense, the practice, okay, of what you're going to be doing. And we want to first just start talking about some basic notions in statistics to try to understand what it is and what it is that you'll be doing in statistics, because it's a very, very broad field. So there is no official definition of statistics, if you will, but most people agree that statistics primarily consists of three activities. It is the science of collecting, organizing, and analyzing data. Okay, those are the three things that we do in statistics. Now let me make a few comments about this definition. First, you notice that data plays a central role. Statistics is data driven. Without data, you have no definition, okay? Because what is the collection, the organization, and the analysis for? It's being done on data, okay? And it's always important to realize that. And that's why we say statistics is really the practice of probability, okay? Because anytime you have data, you're doing statistics. We're going to focus primarily on the last aspect of statistics, the analysis. And very often when people talk about analysis, they're talking about inference, okay? And I want to talk a little bit about what inference means. Now, what is the general meaning of the word inference? What does it mean to infer something? Okay, well, to infer means that you look at a few cases, or you look at a limited amount of empirical data, and you try to generalize. You make a generalized observation, right? So, for example, the existence of God, that's an inference. We can't prove it, but we look around and, oh, you know, who made the trees? Who made the this? You know, who did this? And, you know, I have this sort of feeling. And then based on all these things, people might conclude that God exists, okay? Now, how does that work in statistics? What is statistical inference? Well, it's a little bit different, but it's the same sort of idea. We're going to draw conclusions about a population. That's our generalization. We're going to generalize to the population based on a sample that we draw. Okay, that's going to be our limited empirical observations, if you will. Okay, so we're going to take a sample, we're going to study it, and based on what we see from that sample, we're going to generalize it. Now, one thing I should say is that science is basically inference, okay? It's important to understand that statistics is really a science, because this is how science works. Science is all inferential, right? You drop one apple, you let go of one apple, it drops. You let go of two apples, it drops. You let go of three apples, it drops. And you say, after a while you say, well, after the 20th apple, there must be something that's causing the apple to drop, okay? But we can never prove it. We can't prove gravity, okay? But we can infer it from our observations. So statistics is really more of a science than it is a branch of mathematics, because mathematics is purely deductive, okay? All right, so what are the types of statistical inference we're going to do? How is this going to actually work? So there's a couple of things we can do. First of all, we can try to determine the distribution of some random variable. Okay, we might have a bunch of random variables, we plot them, and we notice that the frequency distribution appears to follow an exponential distribution, and we might say, based on the sample, we're going to conclude that this is an exponential random variable. But we have ways to test if that's true. Just like in the scientific method, we have ways to test if something is true. We're going to find that there are ways to test this sort of generalization. But there's other things going on. Notice that you might plot something and see a nice bell-shaped curve, and you might say, well, that's a normal distribution. But we're going to see in a little while that in order to work with a normal distribution, you need to know a lot more than just the fact that it's a normal distribution. You need to know the mean and the standard deviation. Those two numbers, those are what we call parameters. Those are numbers that characterize the distribution. And so we may want to get estimates for the parameters of a distribution that we know what type it is. Okay? There's lots of other things we can do though. We can do straight up hypothesis testing. This is where we are testing a hypothesis about the value of a parameter for a random variable. So we might have some belief. We might say we think our favorite sports team should be above 500 this year. And then we can go ahead and we can test that belief. Okay. And finally, and this is what is most important to you, is the notion of model building. Okay, so we're going to create a statistical model, not a mathematical model, but a statistical model that's going to look at the relationship between several random variables. And so machine learning does this. A lot of branches of model building do this, but the most basic one to start off with is linear regression. We really want to try to understand linear regression well, and then based on that we can begin to understand the other types of model building. But this is something very central to most advanced types of inference. So it turns out that in most of these different types of inference, we're doing hypothesis testing. So let's go back to this analogy with the scientific method. Okay, we want to infer something and we have to use the scientific method to test it. Well, in statistics it's the same sort of situation. We have some sort of generalization we want to make and we have to perform a test. Just like we use a scientific method in science, we use hypothesis testing in statistics. And here's some different ways that works. I want to go back to the examples I talked about before. So this is something that is used in all types of inference because it's a very basic way of testing our generalizations. And so if we're looking at generalizing something about a distribution and we want to try to determine what type of distribution we have, we can use a chi-squared hypothesis test. Okay. If we're looking at the confidence interval for an estimated parameter, so whenever we estimate a parameter, there's going to be errors. We put an error bar around it. That's generally going to come from the central limit theorem, and that's something that pops up in hypothesis testing, although it's not a hypothesis test in and of itself. Sometimes we're just doing straight up hypothesis testing. Okay, you have a belief about what you think the mean of some distribution is. You collect a sample and you test it. Okay, and then obviously it's being used. And last, in model building, there's a lot of different ways it comes in model building, but the most basic is when we look at the noise or the error term in modeling. So notice that we said the model that we're going to make here is not a mathematical model. It's a statistical model because we put a noise term in, an error term. And so it turns out that very often we need that error term to be normal. There's a lot of theoretical reasons and practical reasons why that should be. And so we have to do a hypothesis test to see if that error term has a normal distribution. And so this kind of goes back to this original problem here, looking at the type of distribution. Okay? But there's actually more sophisticated methods for the normal random variable than chi-squared hypothesis test. There's much more sophisticated ways of doing this. Now, a key player in hypothesis testing is that well, let me back up a second and just kind of explain how we're going to do this hypothesis testing. So we're going to suppose we have a random variable. We're going to generally call it capital X. It's going to come from a certain type of distribution. And so let's suppose that X is a normal distribution, a mean of 0, a standard deviation of 1. Okay, so we know that it's normal. And we're going to make a hypothesis on the mean. Okay, so here the hypothesis is that mu is equal to 0. Now how do we test that? Well, we collect data, right? How do we test the hypothesis in science? We collect data. In statistics, we collect a certain type of data. We collect what's called a random sample. And in a random sample, it's a very special sort of sample. It's a sample where the values are independently chosen. Okay, so I'm going to choose small n values, data values. I'm going to reach into a bag. I'm going to draw out small n values. But I'm going to do it in such a way that those values are independent. Meaning that whatever I chose for a particular excuse me, random variable will not affect the next random variable that I choose. That's what independent means. Okay, so you could think of it as, you know, you stir up a bag of values. Okay, draw one, put it back, okay, you know, record its value, put it back, stir up the values again, reach in the bag and draw another one. Okay, that would be independent values, right? Okay, and the idea is we're going to compute a test statistic from that random sample. Now, you have to know what the word statistic means. A statistic is anything that we compute from data. And this is called a test statistic because this is going to be used to test our hypothesis. So this is a statistic, something computed from our random sample values that we're going to use to test the hypothesis. Okay, and in this case we're going to show later that the test statistic for the population mean mu is the sample mean x bar. Okay, that makes sense, right? The sample mean should be our best estimate of what the population mean is because we're estimating the mean of the sample. Okay, what do we do next? Well, this is very important. The fact that we know the distribution of x is going to tell us the distribution of x bar. And this leads to the notion of a sampling distribution. So I want you to stop for a minute and think about something. These n sample values are random variables. I can't know what they are until I choose them. So every sample is going to be different. Okay, they're going to have a different n values. So because the sample is a random sample, x bar is going to be a random variable. X bar is not going to be the same from sample to sample. If, for example, let's just take an example. It's not particularly relevant to this because the mean won't be 0, but suppose you were looking at heights of people and n was 10. And I go out and I choose 10 people and I take the sample mean. Okay, x bar 1. X bar for the first sample. And then I put those people back in, I mix them all up, and I choose another 10 people and measure their heights. Is the second x bar going to be the same? No. Most likely it won't be, right? So the main thing you want to understand, this is very important, is that the test statistic itself is a random variable. The test statistic is a random variable. And all random variables have a distribution. Therefore, the test statistic has its own distribution. Let me say that again. Okay. The test statistic is a random variable. All random variables have a distribution. Therefore, the test statistic has its own distribution. Okay? And that distribution is the sampling distribution. Okay? This is the distribution of the test statistic, assuming that our statement about the distribution of x was true. Okay. This is a very important point. It's the most overlooked and most misunderstood part of statistics. And it turns out, we're going to show this, it's not hard to show, we're going to show that if x in fact comes from this normal distribution, x bar also comes from a normal distribution. Has the same mean, but the standard deviation from the population is divided by a factor of square root of n. Okay, and this is called the sampling distribution of X bar, this part right here. And now we're going to make a hypothesis test, and this won't make a lot of sense until we get to the next section, but basically we're going to say that if we come from this distribution, given the value of X bar we have, how likely is it that that test statistic could come from that distribution? Okay? In other words, if I assume this distribution and the value of X bar comes from the first percentile, it's not very likely that X bar came from that distribution, because there's only 1% of those X bar values that are less than it. It's an extreme value, right? So this kind of goes to the notion of how do you determine how likely a value from a distribution is? How do you determine how likely the value from a distribution is? You compute its percentile, right? If somebody's height is in the 99th percentile, what does that mean? That means only 1% of the population is taller than them. Is it very likely to get a person in the 99th percentile? No, it's not. Okay? So the percentile tells us something about how likely we are to get that value. And that's how we're going to determine if this is really true. We're going to assume that X bar comes from a certain distribution, actually look at the value of X bar that we have, determine the percentile it would have in this distribution, and on that basis determine how likely it is that our original assumption was correct. If we get a value that's too extreme on either side, its percentile is too low or its percentile is too high, we're going to say it seems unlikely to get a value that's that extreme, therefore our original assumption was wrong. It's like proof by contradiction, isn't it? Okay? Now, so this is the key point. Extreme values are less likely to be observed, and we're less likely to believe our original assumption or hypothesis. Now, a key player in all of this is a normal distribution. It's central in practically all inference. It's hard to emphasize how important a normal distribution is. There's a couple of ways it's used in our particular problems that we're interested in here. The first is the central limit theorem. And I'm going to actually state a more general version of the central limit theorem. Okay, but the central limit theorem is usually what people think of. But it also comes up in the chi-squared distribution when we are doing a goodness of fit test to see if a distribution is a certain type of distribution. So we have something that looks like an exponential distribution. We want to see how well it fits an exponential distribution. So we use a goodness of fit test, and some of those are chi-squared tests. We use a chi-squared distribution. How is that related to a normal? Well, the sum of appropriately scaled independent normal random variables is a chi-squared random variable. Okay, and so we're gonna look a little bit at that maybe. Okay, so now we're going to talk about normal distribution in the next section.